JWC Environmental. I am in their research and development department. I'm one of the senior R&D engineers. My preference or strength with the department is control philosophy type stuff. So when we have a new product or some modification to an existing product, I'll write the control philosophy based on what I see that the application might require versus what our equipment can actually accomplish. And then I'll send that over to the motor control design engineers who will then create the hardware and then ultimately do the PLC programming and operator interface programming that goes along with that. So then I end up in this type of situation where I'm working with the customer to try to ensure that all of that works right. And I don't always get it right out of the gate. We don't always get it right out of the gate, but certainly we want to try to make sure that it's as close to what you need as reasonably possible. So. I've been with the company since 1997. I did take a 2-year break to go help a guy run a vintage race car business for a little while. That was certainly a lot of fun. But we grew too much and he got a little antsy, so he let me go. Has anybody ever been laid off? It's really unsettling. I'd never had that before. It was really unsettling for me anyway. So JWC Environmental produces a bunch of different products. You know our Muffin Monster. I'm sure you've probably heard that name before. It's pretty common in the marketplace. And we also produce machines for, well, these screenings washers like you have here. We make septage receiving systems. You know, like over here at this Headworks, you've got that septage dumping point. We make a machine that will receive that material, shred it, and measure the amount of volume that flows through a flow meter, and then cleans all the screenings out of the material, the chunky bits, right, that you're trying to take out on the back side of the bar screens. We can take that out ahead of time, and then allows the organics and the liquid to flow into the Headworks. Meanwhile, we've just kept track of all of the flow, and so now we would provide that information to you guys, and you could bill the customer based on the almost exact volume, right, that they're discharging. The washer compactors fit in any of the applications where there's a screen that's pulling material out of a waste channel, and whether it's our product or a competitor's product or a long-time existing product, we want to be able to help. Well, we want to make money, right? I mean, that's what we want to do. And so we'd like to be able to help solve your problem and make some money at the same time by getting a piece of equipment in those applications. And the objective, of course, is receive all those screenings from that feed device, whatever it is, whether it's a fine screen, a perforated plate screen like you have over at RP4, whether it's 1-inch mechanically rigged bar screens like you have here at RP1, or whether it's any number of different things that might fit in between there. The washer compactor can pretty readily plug into those types of applications. We just need to understand predominantly what the size of the machine is, what kind of clearance there is off the discharge, and ultimately what kind of throughput we need to be able, or capacity we need to handle, and then we can size the machine accordingly. And the name washer compactor is, you know, intending to illustrate exactly what the thing is. It's intended to take the material, wash it, and then compact it with the objective of also dewatering it, so that you have not only a reasonably clean product, that doesn't really sound right for dealing with this kind of stuff, does it? And a reasonably dry product that goes in the dumpster. Our objective is to try to get to the point where what's sitting in the dumpster either passes the paint filter test at a minimum, is our desire, or that we can get somewhere in the neighborhood of, let's say, 30–35% dry solids. That would be our desire. Sometimes we have customers, engineers that spec must have a minimum of 50% dry solids. And we did that once, just before the machine broke. It really is very difficult in this type of technology to be able to deal with product that's that dry. And it's amazing to think of too, isn't it? It's still 50% water, yet it's so compact, it's so dry, that it becomes difficult to convey, compact, and things of that sort. I did not bring a specific training program. I tried to get one yesterday, but we hadn't had one prepared ever, evidently, to really walk through the details of this from a training perspective. So I have what our tech writer provided me, which is more of a sales and marketing thing. I don't intend to try to sell you guys. This is not what I'm trying to do here. Just want to use this as material to be able to convey certain concepts. So let's flip through here and see whether or not there's some stuff that we can work with. Well, this should look familiar, right? You've got these machines at these two plants. I've seen them both. Hopper, grinder. This is the washer compactor itself. We call this whole thing a screenings washer monster. We have our monster family of products, right? So we started with the muffin monster, and then we added the channel monster, and then somewhere in there the mini monster and the macho monster and the auger monster. It just goes on. We like this family of products. So now every time we get a new product that's on the municipal side, everything gets a monster name. And how many people here know of the muffin monster? Right? It's a pretty common sort of industry term, and we're proud of that, as you could well imagine. So we continue to try to kind of lean on that sort of marketing aspect. So with this guy, what have we got? We've got a grinder with a motor and a speed reducer. We've got a drive on this end that operates the auger on the inside. This is got an inspection port here, so you can look down and see what's going on. This was, in fact, one of our prototype units. As you'll see from your units, you've got an inspection port both here and over here on the drive side of the inlet to the tank. There's this spray wash system here that's responsible for pushing wash water into different places, and we should be able to cover that a little bit more as we move forward.
Todd, before we go on too much, if you go back to the previous, you said that the two, well, the one at RP4, the one here, are different than the two that are down at RP5 and Carbon Canyon.
Are they?
What is the fundamental difference between?
I don't know, because I don't know what's at Carbon Canyon.
Okay.
I don't. If you could have someone pull something that
exactly
references.
the same. I just remember through conversation with you that.
Okay. All right. I don't recall Carbon Canyon and understanding what is there. At least it doesn't come to my recollection. We have 3 different versions of our screenings products. The big daddy, as we would kind of affectionately call it, or at least I do, is what we call the SWM-XE. We produced that because the former owner of the company said, "I want you to build tanks." So we built this thing with a lot of steel in it. And it's got a lot of features on it, and as a result, it is not inexpensive. So we gave this thing to our screen team, the same team that would have sold you the 2 screens at RP4. And they came back to us and said, you know, those are very nice, but we have to sell them for quite a lot of money. Can we get something that's more cost effective? And so we produced the SWM-XEM. I don't know why M. I still can't figure it out. It's a smaller unit. It still has this sort of cylindrical tank kind of shape with the screw and the brush in the inside and perforated screen, which they all have. But it's smaller and it's more cost effective. And then they came along and said, well, yeah, but that one's still a little bit too pricey for our customers. Because bluntly, the problem that we have in the industry, while we try to sell our perforated plate screens and we try to sell washer compactors with grinders, because we believe the grinders are very helpful in breaking up the material that's come off the bar screen, that's come off the fine screen, that's come off the whatever screen, so that we can actually expose the organics to the wash water so that they'll wash more readily from the material. So our competitors don't tend to like to sell grinders because they don't have grinders to sell. So unfortunately, the price point in the marketplace for a system is often a little bit lower than where we would be while trying to sell a grinder as well, right? Because there's this net add of an additional piece of equipment that requires maintenance, of course, and that type of stuff. So anyway, we came up with a yet more cost-effective version that we just call a screenings compactor monster. And this one is not really intended to do much washing. It's still based on the same sort of drive auger rotor technology, elbow, discharge tube type stuff. But again, it is a little more cost effective. So there are these different options certainly available, and that's kind of the progression of how we got to today. Let's see, you guys all know what crappy stuff looks like. Smiling faces. Let's see what we got. Oh, this is all fancy. This starts getting closer to what, well, this is pretty good for what we'd like to see coming out of these systems. Can I tell you a story? We have a customer here in California that bought 2 screens and a washer compactor from us. And when the whole system was put in place and was operating, they really didn't like the resultant product. And at a certain point, our field service guys and customer service asked me to play a role in it. And I went to take a look, and it's true, it was pretty dirty. The organics weren't really being washed out that readily, because they actually had somewhere around 2 to 2.5 minutes between screen run cycles, at best, in order for us to be able to take the material, wash out the organics, and then move it on. And there just wasn't enough time to do that, to work that process adequately. And we get that sometimes, is that the application produces so much material with some other parameter restrictions that make it difficult to actually get this type of product. That customer wanted a product which they never identified in their specifications to be white and fluffy. They believed that it should be white and fluffy. If you guys ever come out saying that you think the stuff should be white and fluffy, I'll come and personally have a chat with you, because it's just not possible. It's not. I don't know where they got that perspective, with the exception of that one occasion where we did get some pretty white material that happened just before the machine broke. Remember I was telling you about that? Of course, marketing likes to use that stuff, right? So they put it straight on their marketing material saying, we can do this once. Anyway, this is more representative. It's a kind of a gray in color. So we've got most of the organics out. Otherwise, it would be more brown in color, as you might imagine. And that's what we strive towards, providing, of course, that the application will allow for that. And that means that we need time between run cycles of the feed devices in order for us to be able to accomplish that kind of product. Let's see now. Keep going. Reductions in, I don't know, if you see something I should talk on a little bit more, guys, let me know. Otherwise, my objective is to really look more towards what this group is likely more interested in. This says movie starts automatically. So we have this animation. It's a separate file that I've got, and I'll go get that and run it. And it actually kind of gives you a better sense of what goes on inside the system. I have to dump out of this for a moment. I try to impress. So here we've got material. No! Stop, 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 stop. I'm not duplicating screens. Alt F4. Duplicate. 4, 3, good. So here you see material coming from somewhere, whatever it is, a bar screen or otherwise. It drops into the hopper. The grinder now shreds the material, and that drops into the wash tank of the washer compactor. Wash water is added here. The material is pushed towards the discharge elbow. This rotor ends. Pause. Can I pull this back? This rotor, this spinning screw piece, it ends somewhere about here. We stop conveying material at about this point, and we start piling the material on the inside of this elbow piece. As the material piles and piles and piles, it starts to compact, and it forms what we call a plug. And you see the plug emerging out of the tail end of the discharge piping as it drops into the dumpster. But the plug is formed here at the end of the screw. everything that's important about the way this machine operates as far as the drying and formation of the plug happens right there in this section. Everything else beyond here is all essentially a consequence of what happens at that point. So if we can manage what's going on there by ensuring that we present that area with clean product or maybe a little bit dirtier product depending on what we're trying to accomplish, and that'll make more sense as we get further into this, or the longer we allow the end of the auger rotor to rub against the face of the plug. Can you picture a pipe, right? And it's got stuff in it, and that stuff it forms like a wall of sorts, right? I'm calling that the face of the plug. So the material gets conveyed off the end of the screw to that point, forms the plug, and that face of the plug is what we want to try to manage. So let's see if we can keep this going. So then the material compacts through here. It stops compacting certainly by here, and we have a tapered tube that relieves the friction against the plug. And we produce the plug at about 12.5 inches. That's the ID of that tapered tube right there where the plug is formed and through that elbow. And then we fan out to about 14 inches, right? So we should end up with 14 minus 12.5 is 1.5 divided by 2 is 3/4 of an inch all the way around the plug of clearance. And that's typically enough to allow that plug to expand a little bit to relieve any compressive, relieve of any compressive forces that it had, and now just pass along throughout whatever the discharge piping is. You can imagine, though, that the longer the discharge piping run, the more we're pushing a lump of material, right? So if we've got a short pipe, let's see if we can get this guy going again. If we've got a short discharge tube, then, and that discharge tube, of course, it's always at an upward angle so that we can make that pile in the elbow, then we've got gravity to fight against as we try to put more material in there and we try to push that material up that elbow. Oh, you can see here where the liquid and organics are coming out. Right? So if you're taking material down here and you're pushing it up the elbow, not only do you have the friction in the elbow to deal with, the motor power is going into pushing the material through that elbow, but it's also going into lifting the material up through the piping. And then you've also got any friction between the material and the inside casing, right, of the pipe. And the longer that is, the more friction you've got and the more power we're going to consume. So that's one thing we want to be careful of when we're picking operating parameters for the equipment, right, is what's going on? What are we feeding into? Is it a short discharge? Is it a long discharge? Do we have a lot of time or a little bit of time between run cycles of the feed device in order to be able to do what we want to do? Does anybody have any questions about this sort of operating philosophy of the overall machine itself? Okay. Recounting or recovering what we've already talked about, right? Hoppers. Hoppers we make based on the application. It's not expected to be a one-size-fits-all thing. The grinder here in this case is what we refer to as a Macho Monster or our 40K series product. We can also use a 30K series product in this case as well, which is 5 horsepower motor instead of 10 horsepower. These grinders have got bearings on the shafts, and there's tungsten carbide mechanical seals on those bearings to be able to keep the wet on the wet side and the dry on the dry side, if that makes sense. And we don't care if these things run all day long or not. That's fine, right? So the grinder can run and run and run. The only reason to really shut it off is potentially for energy savings, right? So obviously you've got a 10 horsepower motor running and it's consuming, let's say 40% of its rated power, 30%, I don't know, what would be the no load consumption of a motor, right? It'll just consume that power spinning those cutters around. So we could shut it off, and that's what we usually do with this product. The auger's in here. Here's the motor and speed reducer that drives that again. The liquid comes out here and on the far side. We had it at RP4 where it appeared as though we weren't allowing the water to escape adequately from the wash tank, if we could call that a wash tank, we had one of the 4-inch drains piped in, and it was doing not a bad job, certainly everything it could. But when we opened up the other drain and all this water was coming out there too, we came to realize that we've got all this organics-laden water inside that tank that's just not escaping. We want it to escape. There's a perforated screen that's cylindrical on the inside of this thing, where there's this rotor with the brush on the outside of it to keep it clean. And we prefer to have that water level below that screen. Otherwise, that water is just taking all of those organics and pushing it down towards the plug at the discharge end. And now we're going to have a really hard time getting the product clean, or at least keeping it clean. Let's see. Grinder, we talked about the fact that the grinder breaks up the material that comes off the bar screen or the fine screen so that we can get those organics out. We have spray wash water on the inside of the tank. It's not done this way with the washer compactor. This is in fact an illustration from one of our inclined auger screen products. And when I say inclined, it's what we call our auger monster product. But what we do have is we've got this series of holes drilled in the tank, and then we weld over it some angle iron and we seal it off on either end and we push water in there, and so we get this water that shoots in from the outside of the cylinder towards the center. Although as we were talking this morning, there is like a bit of a concern there, because the water, if there isn't material in that flow path, the water is going to hit the center pipe on the rotor, and then it would run off the center pipe and then it would land on whatever material was on the screen. So we don't get the benefit of that, the energy of that water hitting the organics directly in that particular case, not unless there's enough organics in there that water can actually impinge upon it. Let's see, triple zone spray wash. So we have potential for spray wash in the hopper. We have spray wash in the auger tank area, and then we also have spray wash to wash out the under tray, if you will, of the tank, or under the screen. Sometimes we can get material, sediment, grit, that kind of thing that might build up down in here, and so we found that for this model we like the idea of being able to wash that stuff out. You see this hose? Hopefully we'll see it illustrated as to what that goes to. I'm sure you've seen it at either plant. On the elbow, the discharge elbow, there's a water injection point or two. And that is intended to be able to wet the plug in case it gets too dry. We have this thing we call a smart controller. And the idea with the smart controller, and both of the two systems that are at, well, RP1 in here, use this. Well, we did manage to trademark it, this philosophy for operation. And what it basically says is, if we monitor the power consumption of the motor, we can kind of get an idea of what's going on where we're forming the plug. In fact, one of the guys I work with, when he was doing it, he was looking strictly at current, not power. And I know they're quite related. I think power is just a little bit more accurate as far as trying to take a measure, but he would always tell me current is the window to the elbow, right? So we have this elbow and we're forming a plug there, and the more dense the plug is and the more dry the plug is, the more current is going to go up, right? The wetter the plug, the more organics in it, the likelihood is the current's going to drop, or conversely, power up, power down. So what we do is we put a power transducer inside the controller. We watch the power being consumed. Well, no. We watch the current on all three legs of the load side, right, of the contactor. And we also monitor the voltage difference between all three legs. And we use that to determine power, and we communicate that back to the programmable logic controller. From there, what we're able to do is we're able to, I'm just going to have to stick with this screen. We're able to set operating parameter stages, we call them, so that depending on how much power is being consumed, we can affect than how much, well, what the run cycle is, or what the wash water parameters are, that type of thing. So if we're consuming a little bit of power, we could probably wash the product more and dry the product more. If we're consuming a lot of power, maybe more like upwards of the motor's rated power, if there's a 3 horsepower motor, then 3 horsepower or 3 times 746 equals 2,400 some odd watts, right? Now we're saying, motor's working too hard. Or if we have a 5 horsepower motor on it, then the number is going to be something closer to 4,500 watts. So if we're consuming closer to 4,500 watts, we're going to ask the equipment to work differently than when it's only consuming a little bit of power. So what we did was we created 4 stages of operation. Stage 1 is in play between 0 and 50% of the motor's power. Stage 2 between 50 and 75%. Stage 3 between 75 and 85%. And stage 4 is the, it's going wildly wrong, between 85 and 100 or whatever number could come back from the system. We don't want to be washing it and drying it a lot at that point in time. We want to be ensuring that the material in the plug and at that plug forming interface is swapped out for something that's too clean and too dry, for something that's a little wetter and a little bit more organics laden, because the organics act as a lubricant for the material, believe it or not, right? And allow the material to slide a little bit more neatly through the elbow. We'll come back to that one in a little bit. Let's see what else is in here that we could work with. Let's see, scrapers. Is there any maintenance staff in here, or is this all operations?
All operations.
All operations, right. So just so that you're clear, we have these scrapers on the cutter stack. So if you're taking a look in the machine and you're seeing that there's a lot of material buildup for some reason in the grinder cutter stack, then there may be an issue somehow with the scrapers. Or maybe the grinder doesn't actually have scrapers on both shafts, or it doesn't have scrapers on the shafts. For this type of shredding type application, scrapers tend to be very beneficial, and we try to ensure that they're on all the new units that go out. COD before, after. That's an interesting one, right? Here's a couple of applications where we've done some testing. Czech Republic. Yeah. I've done some more recent stuff, and it does actually show that we can reduce the organic content using BOD measurement, probably by at least 50 to 75%, sometimes better. Dry solids. So here's some examples. See here, just before it broke, kind of stuff. I'm kidding with that, you realize. Let's see, roller base. The machine at RP4 has a roller base, right? The one here, does it have a roller base too? It does, huh? Okay, so that's good. So you can move it out of the way, get a dumpster under it if you have to, right underneath the conveyor discharge. Baggers, you guys produce too much material, I think, to use a bagger. I think just directly into a dumpster makes more sense. Let's see, can work. Headworks, don't care so much. Here's some examples, though, of product. It's coming out of washer compactors at different places.
System on that previous slide? Sorry, go.
That's bagging. This is interesting. That doesn't work. Sometimes application engineering has to learn the hard way. Well, let's take a bagger and connect it to the discharge of a pipe that's pointing up in the air. They learned the hard way in that when this thing went to the customer, I don't know if it was this application or not, but it could well have been, and they put the bag, you guys know this product? This is by a company in Sweden called Paxo. It's their Longopack series. So they have these plastic parts, and they make their money selling the bag material. And it's this accordion folded plastic sleeve that comes in a box, and when you open it up, it forms a ring. It's got ties on it, and you take that and you stick it somehow on this tube that's behind this thing, and then you put this piece on, and you're supposed to put this on from below to hold the bag, and then you pull the bag over top, and so now and tie the end, so that now as material falls in it, it drags the bag down and fills up until you've decided it's big enough. You grab it, pinch it off, tie off that end, cut it, tie off the bottom of the next one, and now it just keeps adding. It's like a diaper genie, right? It's like a diaper genie. So what happened here was that when they put the bag on, got it on, the entire bag slid down the tube. Didn't impress the customer very much. So no, these things always have to be at least mounted so that this plane is vertical, or preferably that it's pointing downwards. We can manage 90-degree elbows like this. That's okay. You don't have that on any of your applications. Sometimes it gets a little bit. Oh, you do. RP4 has the elbow like that, doesn't it? The tight elbow. I'm thinking it does. To go back to pictures.
Oh, it does. Well, maybe not.
I got some photos. We could double check if we really cared.
I thought it was more like that.
More like that? Okay.
I think it's just they cut the opening in the pipe to come out the side.
Ah, all right. That was that screenings, septic receiving system I was talking about. Grit, grinder, flow meter, plug valve, tank.
Can you add EC and conductivity to that? All right, EC and pH to that?
pH and conductivity are the two things that we can readily accommodate. EC.
No, that's it.
That's it?
pH and
Yeah,
conductivity.
we offer that.
How much do those things run typically? Are you talking like hundreds of thousands of dollars?
What, that system?
Yeah.
That's 100K.
Get that on there. Come on, man, budget.
Good. So, okay, so here's your washer compactor, right? So conveyor feeding, hopper with a lid on it, square or rectangular hole in the top. There's wash water feeding the hopper coming through this part of the system. Wash water comes through this hose on the far end through a filter basket that's got a 20 mesh filter in it. That has to be checked periodically. It can come up. Then there's should be an 80 mesh filter or maybe a 100 mesh filter in this Y strainer. That needs to be checked periodically because it too can gum up. The solenoid valves here are pilot operated, electrically actuated, pilot operated solenoid valves. And they have
Solenoid monster.
a solenoid monster, there you go. They have a little water flow path in there and a little spool, and the spool is drawn up and down by the coil, right? Sometimes the coils burn out, so if you're not getting wash water to a particular area, it's important to check two things. Maintenance is going to care about this more so, but it's important to check two things. One is that there's no material that's plugged up the pilot circuit, and the other is that the coil is actually still able to energize and move that little spool. Those are the two things about a solenoid valve that could be a problem. And sometimes I find one may be an issue. Typically the plugging of the pilot circuit is the key one because reclaimed water at different facilities it's clean to different levels. Here I understand it's quite drinkable, so there's no real harm in ensuring that it will flow through this properly. It's not drinkable?
Sure.
Let's see. So here we've got the main screen. You see the grinder's running. It's green, showing it's pulling about 8.5, 8.6 amps. Auger's stopped. We have this accumulated feed time thing. We've got a variety of different parameters that affect the operation of the machine. When we originally came up with this product, we introduced something we called a start delay. And the start delay says, when the feed device turns on and stuff is moving in the direction of the washer compactor, we want to wait for some period of time before we start the auger through its run cycles. We want to do that because we don't want to start the auger running through run cycles before there's material there to make it worthwhile running a run cycle, if that makes sense. So the start delay says, oh here, this is the start delay parameter. It says, wait, okay, now start the run cycle of the auger, right? Now we do whatever the run cycle is going to do, and we stop, and wait for the next cycle of the feed device. The accumulated feed timer was created because we had an application one time that started it anyway in Wisconsin, where every time their feed screen ran, it only gave us a really small amount of material. So if we would run the auger through a run cycle every time we had a really small amount of material, it's going to be very easy for the machine to wash and dry that small amount, right? So what we were seeing is that the elbow was plugging up. There was too much friction in there. The power consumption at the motor was rising to be excessively high, and so we would end up with a situation where we would lock up the elbow. That's the term I put to it, locking up the elbow. You guys have had that experience here, I understand, one time. Hopefully never again. The concern then, or the way around that, was to say, we're going to introduce this retentive timer that says, we're going to allow the auger to receive, or the washer compactor to receive material from conceivably multiple feed screen run activities. So let's say this feed screen at some application might run, RP4 is like 25, 30 seconds, something like that, right?
I think it's 0 now.
It's 0? It's running all the time?
Or 1 second or something like that.
You're talking about the accumulated feed time value? Okay, I was referring to the amount of time that the feed screens run.
Oh, yeah, 90 seconds.
The feed screens run for 90? That's a lot longer than we had it before. I'm kind of surprised at that. Okay, I'd be curious to dig into that more. So let's imagine that in a minute, we only got a little bit of material off the feed screen, right? Well, it might be beneficial if we could collect material from, let's say, 5 cycles of the feed screen. So if we set the accumulated feed timer to 5 times 60 seconds is 300 seconds, then that essentially would allow the feed screen to start and run and stop and be off and start and run and stop and be off for 300 seconds of run time before the washer compactor would do its thing. All right? This can be helpful in other circumstances as well, like here at this facility, where those 4 bar screens can be running either at the same time or at completely staggered times, depending on how the control system is operating. Because they're independent from one another, right? We try to dial them in with those timers and the like, but that's like trying to, well, we were talking this morning about synchronizing watches, and if those timers don't stay on sync, then we could see a run permissive signal coming from any one of those screen controllers to the washer compactor controller at any time. Well, if we're initiating a run cycle, every time we have a signal coming from, a run permissive signal from one of the feed devices, right, the band screen or bar screen controllers, this thing could be running one heck of a lot of time. And if we're not getting much material off the systems, then we run the risk of over-drying the plug and locking up the elbow. So that's what the accumulated feed time is about. So start delay says run the screen, wait for a period of time, then run the auger. Accumulated feed time says collect up a certain amount of feed time in sort of a bucket, and once the bucket is full of time, then run the washer compactor. You can see here how that setting for the accumulated feed timer was set to 999. That's typically kind of a maximum value for us. Often that's what the PLC programmers do, is they'll pick, for 4 characters, they'll allow the maximum value to be 9999. Even though the number we would typically put in there would not be 9999. And it's a bit unusual here for it to be that long. We calculated this morning that's about 15 minutes. It's a fair length of time to be capturing material with the screens running. And it's in fact the conveyor that should be the thing triggering us, right? The conveyor is going to run when any one of the screens is running. We're going to be watching the conveyor whenever it's running. So if it's running, we presume that it might be delivering material to the washer compactor. So we want to count how much time it's been running before we initiate a run cycle of the washer compactor. Let's see, page down. when this system started up, after that 999 seconds of accumulated feed time, we see the grinder is still running at about 8.6 amps. The auger starts off in this first forward time element. Anybody offer some input in terms of what the run cycle time elements are for this equipment? Guys have any familiarity with that? What we do is we initiate what we call a run cycle, and the run cycle consists of 5 time elements: a forward, a stop, a reverse, a stop, and then a final forward. The idea with the forward is we want to take the material that comes in from the grinder once it's piled up below the discharge end of the grinder, side of the grinder, and we want to move it inside the unit with wash water pouring on it to try to agitate it to some degree and to get the wash water to help soak and break up the organics. Soak. It just came out of a wastewater channel, right? So I'm not sure that there's much soaking going on. And then we stop for a bit and let the wash water pour on it. So forward and a stop. Then there's a reverse. And we want to limit how much we reverse, because if we reverse too much, we'll take material and throw it into the drive plate of the machine. And there's a seal up there, and there's a gearbox up there, and all that stuff that we don't want to compromise because we've been packing material in the drive end of the machine. We want material to move in the discharge direction, right? So there's the reverse, then another stop. The stops have a couple of benefits. One is it lets the drivetrain settle, right? If it's running forward and then we energize the contactors in reverse and jam that motor, it's not going to last too long for us. So we usually use about a 5-second stop to let everything come to a stop, and then we re-energize it in the opposite direction. Now we can benefit from those stops by increasing the length of time that the auger motor is stopped by allowing water to flow on the material and help rinse away some of the organics that are in there. So a forward, a stop, a reverse, a stop, and then a final forward. The final forward says, all right, we've had the material inside the wash tank. It's been moved around. It's had wash water flowing on it. We think by this point it's reasonably clean. Let's push it off the end of the screw and into the elbow through that plug forming interface where we can dewater the material so that now as it moves along through the machine, it's the cleanliness and dryness that we hope it would be going forward. So you see here, first forward, we can see what the parameters are. 15 seconds is what the value we're seeing is. I'm pretty sure it started off at 25 seconds and we've actually counted for 10 seconds into that. There's a 10 here, that's the stop, a 15-second reverse, 10-second stop, and a 40-second final forward. It says power is 72% and it's in stage 2. We have 4 stages we talked about, right? Stage 1, 0 to 50%, stage 2, 50 to 75, stage 3, 75 to 85, stage 4 from 85 to 100. So this thing says it's in stage 2. What the system does is it says just as it approaches the end of stage 2, or the end of the run cycle, the final forward run cycle, it grabs the power value, instantaneous power value, and it uses that value to make a decision as to what stage the system will start in the next time it runs a run cycle, right? So if that number happened to grow, and if you think about it, power consumption that we care about is the power consumption attached to when we're pushing material into the elbow. We don't really care what happens during the reverse. Power consumption during the stop should be 0. The initial forward, we're going to push material into the elbow potentially if we didn't get rid of it the last run cycle. So we might care about that, but that's not going to affect the next run cycle. It's the final forward and the power value at the end of the final forward that then contributes to what stage we're going to be in next time. And when we go to the next stage, we get the opportunity to use different operating parameters. Let's see if we've got, I should have taken pictures of all of them. Okay, so these operating parameters are the current one. No, they're not the current ones dialed in. I haven't taken those pictures yet. So look here, stage 1, 2, 3, and 4. Does that look like a fire or something? A chuckle? A giggle? A laugh? A boo? So here we've got the stage 1 parameters, forward stop, reverse stop, final forward, and here's the set point for when we switch to the next stage. So 25 forward, 5 stop, 5 reverse, 5 stop, and then a 60-second forward. 60-second forward. What that means is that for as much as we've pushed the material forward in this 25 seconds, and there's a way to kind of gauge what's going on there. I presume we'll have a chance to walk out to the equipment for a little bit? Unless we can use an image here also to cover the topic. We can kind of predict where the material is going to be based on the time values. So we move the material for 25 seconds. We pull it back for 5. So that means it's 20 seconds to the discharge end. And then we add another 60 seconds onto that. Somewhere in there we have to push the material off the end of the screw, right? I mean, it's not infinitely long. So somewhere the material came off the end of the screw. And we've been rubbing against it with the rotor. The longer we do that, the drier it gets. Can you picture like a wringer washer or wringing out a washcloth or something like that, right? That's kind of what happens here. That rotor, the tips of the end of the rotor, there's 2 of them, they rub against the plug, and as it does it, it squeezes out water. It squeezes out water, and that water runs back towards the screen and through the drain. The longer we let it run, the more dry it's going to be. This number looked to me to be pretty high, understanding the symptoms. And the symptoms are, 1, that you've had to clean out the elbow because it plugged once. 2, that you've had to put a washing system on the discharge piping that helps evacuate the pipe to reduce the power consumption of the motor. And 3, that when I looked at the system, I was seeing power consumptions on the order of 75 to 85%. It's not where we want to be. We should be able to be lower than that. Maybe we have to be up here, but I'm not convinced of that because there are things we can do to try to bring that value down. If we did those things already and we were still at 75, 85%, then I'd get it. But not in this case, all right? In order to be able to try to affect things, what I elected to do is recommend that we reduce this time value specifically, right? I wish I had a photo of the most current settings. I think they read 25, 20, 10, 20, and what's this one? 25 plus 20, 45. And then this one is 25, 10, 10, 10, 25 plus 35. This one has even shorter final forward and only a 5-second reverse. This one has, I think, a 25-second final forward, but no stops and no reverse. And the wash water that we're adding into the tank at that point is a minimal. And we'll talk about wash water in a moment. So as power consumption rises, what do? We reverse less, which means we're moving the material around less in the wash water, and we're tending to push it forward towards the discharge less, right? Because we want to reduce the amount of time that we have the rotor spent drying the material. Here's the wash water piece of that. Again, there's the 4 stages. That one's completely blown out. 30 and 0, 10, 5, 5, 15. Okay, so this is saying that while the auger is running, the wash water solenoid valve for the wash tank is going to be open for 30 seconds and then off or closed for 0 seconds. Open for 30, closed for 0. That would be like a 100% on duty cycle, right? So we're trying to wash as much as we can there. Plus our stops were like 20 and 20. So we're allowing quite a lot of time for, well, reasonable amount of time for the wash water to flow onto the material that's in the wash tank. When we go to the next stage, which is kind of where we'd prefer to be. The philosophy is, let's set up stage 1 to try to drive the system to stage 2. So an excessive amount of cleaning and drying in stage 1 to drive towards stage 2. Stage 2 parameters hopefully are a good steady state. And then when we move to stage 3, we say, you know what, this is a little too clean, a little too dry. Let's allow the material to be a little wetter and a little dirtier so that it drops back to stage 2. What that means is that the motor will essentially typically operate in the 50 to 75% of its rated power band. With that then, stage 4 is hanging out there as a, what is that, right? And the objective with stage 4, as we're already alluding to, is that we want to try to simply move material forward. We want to try to take dirtier material, relatively speaking, and move it into that plug forming interface, right? Because it's what's in there that's going to affect what's going on as far as frictions downstream of that and the motor power consumption upstream, right? When I say upstream, I mean on the drive end, of course. So the parameters we have in there now are, I think this is 75 on, 0 off. That should cover a run cycle in stage 1. In stage 2, we have 15 on, 5 off. So that is 75% on duty cycle. This one says 10 and 10, so it's 50% on, 50% off. And then this one is 5 and 15. So it's off 25, on 25%, off 75% of the time. You see how the way those are set is that as we consume more power, we move to a higher stage, but the higher stage is designed to try to allow the material to be somewhat less clean, somewhat less dry, so that we don't end up with a situation where the plug is too dry to be able to move properly. Now, because this is essentially a closed loop system, it will work to try to find a steady state of operation based on what material is coming in and the rate at which the material is coming in, right? We have the tank flush that we talked about earlier. That's the under tank business. We want to clean what's underneath, so we have this flush time of 30 seconds, and that happens every 10 cycles of the screen. The downside to this, of course, is that depending on when that kicks, and I can't tell you, I think it should kick after the run cycle is finishing, right? So we shouldn't see the water from this flush exercise additive to the water from the washing run cycle exercise. So we'll see that happen periodically. And then we have this elbow, the elbow. Remember we talked before about the discharge elbow and how it's got this sort of couple of taps in it and we can feed water in there? It has two benefits, that thing. We can use it for two things. One is if the thing is powered off for long enough, in other words, there's nothing coming into the system, what we allow for is that after X number of hours, we'll give that thing a little shot, just so that we have some dampness in around the material there. It's not hugely necessary, but we perceived that it was when we originally designed the thing, and we haven't taken the feature out. The second is, as we get to stage 4 and power is rising, when we finish one run cycle, we're in stage 3, maybe we're in stage 2, and for some reason we jump all the way up to power consumption levels for stage 4. Then what we do is we say, when we start the stage 4 run cycle, we're going to give a 5-second blast, or whatever this parameter is, into the elbow, right? Just allowing that we dampen that up a little bit. So it's kind of a belts and suspenders kind of approach to, we've already set the run cycle so that we don't reverse so much. We try to push material through. We've modified the wash water during the cycle so that we don't wash very much. And we're adding a little bit of water to the elbow to try to help promote movement of the material through the elbow. So those are the key things that we're trying to do there. Brush and settings. This is interesting. This is from a different application. Where was I at last? Huh. Let's see what we got here. I was up at Woodland, California. It's near Sacramento, and they were having some fits with the screens that we put in there, and also with the washer compactor, and they were calling up and saying, the product coming out of the machine with your screens on there is dirtier than it was with the other screens that were on there, because we replaced some, I think they were some, I don't know, Parks and AquaGuards or something like that. So what we've got is this situation where the customer perceives that our is causing the washer compactors to produce a dirtier product. The first thing I checked was whether the wash water was flowing into the washer compactor tank. I took off the discharge port on the downstream end. There's no wash water. No wash water. Solenoid valve coil had burned out in that case. They didn't pick it. They were telling us that their UPS was tripping out. Yeah, probably because the coil fried, right? For whatever reason. They didn't ferret that out, right? Which was a problem because now they're thinking that we've left this, we're producing a dirtier product. So what we did was we got the wash water flowing properly and adjusted the spray bars so that in this case it was an older model product, and so we could adjust the spray bars. And we got the spray bars such that the product was now cleaner going into the elbow, so that after 2, 3, 4, 5 days of operation, whatever length of time it takes at a smaller facility, right? These guys are 3.25 MGD, a lot less than what you have here, of course. So it takes multiple days for them to swap out the material in the elbow and their discharge tube. But anyway, that's what's going on here, is that these photos are from that application. So if you'll allow me a moment, I'll see if I can find our specific photos. Yes. What kind of now? Here we go.
No, I think those are the same ones. It's way different than the parameters I took a picture of.
Okay, then what's happening is I'm actually going back to the beginning of the list. So I just need to go backwards through these photos and I'll find them. No? We got this guy. We got that guy.
How about this? Why don't you just plug in my phone? And you could take the
Plug in my phone, iPhone?
my iPhone.
So you got them too, do you? Bloop, bloop, bloop.
Selfies. That is your work phone.
That doesn't mean anything. I have no balance.
What? You're probably going to have to allow something or another on the phone.
I think I allowed it.
Sweet.
Well,
Okay, where do you think we ought to go? Down near the bottom, right?
All right. No.
Further? How many do you think you took? Is there anything here that I can't see as an outsider?
How do you go to X this out? You're almost there. And then go to details.
Details?
So they're right here. And then go to
Look for today?
Yeah, that'd be good.
What's today? 10?
Yeah.
2, 10?
Yeah. And I took 4 pictures. So.
Okay, there you go. So this is what we found when I came today. 25 forward, 20 stop, 15 reverse, 20 stop, 80 forward. Did you take any photos of the washer compactor? Or just the screens?
Just the screen.
Okay. Can you guys visualize the washer compactor? So you've got this thing, there's a drive motor here. I'm standing behind it from what you would normally see looking at it, right? Discharge elbow and the taper tube up here. We've got the rotor on the inside, and the rotor screw has got a nominally 6-inch pitch. 6-inch pitch, half a foot, all right? The screw rotates at about 1 revolution every 5 seconds. So 1 revolution, material would move 1 pitch distance. So every 6 inches takes 5 seconds. That unit is about 40 seconds long, 35 to 40 seconds long. Does that make any sense? So 40 seconds divided by 5, 8 flight pitches, basically. Well, if you consider that the grinder there is a 24-inch cutter stack grinder, 24 divided by 6, 4. 4 times 5, 20. So it would take about 20 seconds for the material to move the distance of the cutter stack. From the end of the cutter stack to the end of the end flange, past the discharge inspection port, discharge side inspection port, that's probably another 20 seconds. Give or take, maybe 20, 15. And then we've got a bit of a distance into the elbow that the auger rotor protrudes with some wear bars around it and stuff like that. That's maybe another 10 seconds, 5 seconds? I don't know, something like that, right? We'd have to go measure it exactly. So what we can say is, if stuff comes in about the middle of the grinder and we run this thing for 25 seconds, 25 divided by 5 is 5 times 6, 30 inches. 1, 2, 3, 4, 5, 6 flight pitches. It's not the whole length of the thing. In fact, it looks as though we would take the material from about the middle of the grinder right to the end of the wash zone. And you can see the wash zone because you can see where those pieces of angle iron are welded on that I mentioned to you that form part of the spray wash manifold. 25 seconds takes the material roughly there. Stop for 20. Okay, that's good. Wash water's pouring for 20 seconds. Reverse for 15. Okay, so bring the material back. 15 divided by 5 is 3 times 6 is 18 inches, right? 3 flight pitches. Cool. It's not quite yet to the middle of where it started because it would need to come back another 10 seconds to get there. But it is actually still underneath the sort of bottom end, the tail end of the grinder chamber, cutting chamber. So what we've done is we've reduced that to 10 seconds. And bluntly, I don't like reverses any longer than 10 seconds anyway. As I demonstrated to those that were at the site at the time, if you have material coming in right at the drive end, well, it's at the auger drive end of the grinder cutter stack, in 10, 15 seconds that material would be pulled all the way back to the drive plate and pushed into the drive plate. Don't really like that, like we talked about before. So reducing it to 10 seconds would keep the material from actually ending up against the drive plate. The reason why I say that is because even though we've pushed material down here, there might be occasions when more material could come in, right? Depending on what's going on with the feed devices. So while we're trying to design this thing so that we manage a batch of material and move it about and clean it and get rid of it, it's possible for other material to be coming in. And when we talk about how to deal with substantially dry material coming in, and I use that as a relative reference. Here, the material is a lot drier coming into the washer compactor than it is over at RP4, where there's a lot of water that's coming off of the fine screens through the conveyor and into the washer compactor with the material. A lot of water. And we have to treat that differently than what we're doing here. In that case, we have to make sure we keep the screen perforations clear. So we have to run the auger through a lot more frequent short run cycles. Again, we'll talk about that more in a minute. So then we've got this stop and then this 80-second final forward. So if we say that from the point at which the material comes in the auger to the point at which it goes, from the grinder to the point at which it goes off of the screw is 25 seconds, I think that's what we calculated when we were out there. We estimated to be about 25 seconds. Let's say we move it forward 25, bring it back 15, and then move it forward again. So no, it was 35 seconds total. This takes us only 10 seconds in the direction of the discharge. So we need to get all the way off the rotor. That's going to take another 25 seconds, or 35 total, like we talked about. And then we can dewater the material for a little while. Well, if we take 10 out of this, and another 25 out of this, that's 40 out. That leaves 40 seconds of dewatering time. We think we know, based on the behavior of the equipment, that 40 seconds of dewatering time with this product is, in this application, is too long because we are seeing excessively dry plugs. So we need to reduce that. We've reduced that to, this number is now 25 plus 45, like we talked about. So we just have 20 seconds of dewatering time. Somewhat less than, right, 50% of what we had before. And then we've reduced this value to 25 plus 10, or 35 seconds. Again, this one is 25 plus 5, maybe is 30 seconds, something like that. And then this one's 25, right? So this is what's going on out there, but before we modified it.
So I'm sorry, there's a lot of seconds back and forth.
Yeah.
So when you take the overall length of the machine and the design of the flights and everything, so your net, so just to move the material off the end of the auger to start the drawing mode is 35 seconds?
That's, I think, what we generally came to when we were out there,
so
yes.
Take all the forwards and subtract out all the reverses, 35. And that should be the same at RP4. And
when you take the forwards and subtract out the reverses,
right,
yeah,
so
what we need is we need a net forward of at least 35 seconds, right? Part of it's going to come from the forward. It's going to be reduced by the reverse. So we have to add that back. And then we have to have an additional whatever time to be able to get the material just simply to the end of the screw. And now we push it off the end of the screw and we dewater.
And the dimensions are the same, so this machine in RP4, that 35 seconds should be the same.
Well,
That's correct.
I thought RP4 was a little bit smaller. I thought this is the largest unit, and that's...
I think the only thing that changed was the motor horsepower.
Correct. That's the 3 horsepower motor, I think, on that one. This one's got 5.
Gotcha.
The actual physical length of the things, I think we call both of them SWM 4024-XEs.
Okay.
If that model sounds familiar for both of them, I believe that's what it is. I didn't actually read it off. Then physically, the size of the things are the same. Now that might be different for a unit that only has an 18-inch grinder on it, because the whole wash tank is 1 flight pitch shorter. So now we have to think that through again. What should our numbers be, and how is that going to be affected by, or how is that going to affect the position of the material, what's going on, and what's happening at the elbow. I think we've modified this to take that number up to about 30 seconds, so we've got some good washing time. I think we took this up to 5 cycles, maybe 10. The elbow spray time, I asked that we take it down to 2 seconds, because 10 seconds of water at 80 psi out there, that's a heck of a lot of water. And we don't want to be wetting the material that much unless it's absolutely necessary. So thus we've aimed to bring that down. And then this periodic spray frequency is up at 99 seconds, 99 hours, because we can't make it any bigger. We don't need to be adding water unnecessarily in there. And like I mentioned before, theoretically we could probably take that out of the program. I don't know how much it really is useful. Maybe there's applications where we can benefit from it. Accumulated feed time is currently, or was at, what's that, 1,000, right? 1,000 seconds, roughly 16 minutes. It looked to me, based on what was coming off the bar screens, what I saw dropping into the hopper, and generally a little bit more about what I was seeing in terms of the amount of power consumption as we got to the end of the first forward and the end of the final forward, is that we were possibly dealing with a little bit too big of a lump of material. And it really works for us that if we have frequent but shorter run cycles, that tends to be of benefit. It seems to pop up with a lot of our products, frequent but short run cycles. So what we did was we reduced this number to 500 seconds. We cut it in half, so about every 8 minutes of conveyor on time, we're going to see a run cycle of the washer compactor. I might make a fool of myself with that. If the auger plug or the auger elbow jams up, call me. I'll be over to help clean it out, right? But I feel like that's maybe a little bit more appropriate to have a more manageable batch. In order to get the product as clean and as dry predictably as I'd like, as I'd suggest anyway, I'd like about, what, 2 footballs maybe worth of product to come in. We can have more, we can handle more, but the more you add, the less you're going to be able to clean it, right? It's just harder to get to all those organics that are wrapped up in that pile. It's not a washing machine that agitates for a significant period of time. It's a conveyor adapted for moving material around with a perforated screen and wash water to try to wash out as much as we can. Right? So if we can manage it so that we collect only about 2 footballs worth of material, what is that? Half a cubic foot maybe, right? And then process that, that's really good. That would be sort of maximum cleaning and drying. As we get more and more material in there, we might have to lean more in the direction of just simply pulling in the material, wetting it as much as we can, trying to wash away as much organics as we can, but then getting rid of it, because now there's more stuff coming in, and we have to be able to handle that stuff. We don't have time anymore just to be able to maximize the cleaning of that particular material. This cycle repetition piece is important because, may I ask that coordinate passing those out?
Yeah, of course.
Would that be all right? So I don't typically go to site unless our customer service and field service guys start to struggle at figuring out what the problem is. This is sort of an escalation process that we have within our company, right? So anytime there's an issue, we prefer that customer service be the front line, and if customer service can't manage it, then they step it up maybe to field service, and then field service would step it up to an R&D engineering, or maybe even the application engineers first, the people who originally laid out the equipment on the job, and then up to R&D. We try not to put too many steps in there because we don't want to frustrate you guys too much. Yet at the same time, R&D isn't available to be able to take care of all of those things. We wouldn't be able to get our R&D work done. One of the things that happens is that each time I go to site and I discover that there is some core issue, then I take that knowledge back to the company, I write a tech bulletin, and I present that tech bulletin to our internal people. You'll see on here in the top right of the first page, there is a sort of for internal use only reference on there. I know what that means in reality, right? It means that that's probably the document that gets sent around first to everyone in the country, as opposed to the one that we say is for open distribution. It's just kind of how it works. We like to ask you guys to generally keep this within the IEUA, right? But this aims to try to help understand, or at least convey to the reader, what we learned as part of a site situation. And this one substantially came to bear as a result of what I learned from RP4. Okay, so I've got 2 more tech bulletins that I need to write. One from Western Wake in North Carolina to help our field service techs and our internal people understand better how to calibrate the power transducers. And I have another one that I need to write on the topic of ensuring that we set a proper datum reference with the ultrasonic probes for our perforated plate screens, our mechanically raked bar screen, or what we call a chain and rake, our band screen, that type of thing. So we go to site, we learn something, we try to communicate this within the organization. In this case, I'm actually able to use it to distribute to you guys so we can talk about it a little bit. I do need one that I can reference though. So what it is that we're trying to do here is we're trying to identify how to set the operating parameters of both the feed screen, depending on your feed screen. It's our feed screen we're most interested in, right? I'm sure you can appreciate that. And everyone's got a different type of philosophy. These screens are on a timer basis. Ours use differential level. This description on the first page under level control is all about configuring the differential level. But then if you go to the second page, and you're welcome to read that, of course, it's just not going to be that relevant to you. On the second page, you see that on item 10, after you get the feed screen delivering a reasonable amount of material to the washer compactor, you've got it turning it on and off properly. Now we have to set up the washer compactor's operation. So we have 2 situations, and we talked about them, right? One where we've got a lot of water that's entrained maybe with the mixing with the screenings, and RP4 is a good example of that. And then the other situation where you generally have a low volume of water, right, which is the situation here. So we have two plants within 20 minutes of each other that have both of these examples built into them. So let's talk about the low volume of water first, right? Let's see now. SCM, let's go to the SMART one, because that's what you've got, right? SWMXE SMART. So you see there stage 1, 2, 3, and 4. Power levels 0, 50, 75, 85. This is familiar, right? We were seeing these in terms of how you're configured here. You see the first forward, notice that now the run cycles are written on the line, not vertically like we had them laid out on the screens here. That's just a difference between how I write versus how our PLC programmers set up the OIT. So the run cycle, 25 forward, 20 stop, 15 reverse. 15 reverse, bloody hell, and I wrote that. I've got to update this document, right? Remember I said I don't like reverses. All right, so we have a washer compactor. On the drive end, we have an electric motor and a speed reducer. Here there's a drive adapter spool that allows us to mount the speed reducer on the machine itself. Inside there's a mechanical seal that keeps the liquid from inside the system from making it to the speed reducer and damaging it. We call this the drive end plate. Of course, there's some lifting eyes. There's an inspection port here. We have a grinder up here, and down here, spray wash supply to the hopper, spray wash water supply to the auger tank, some manual ball valves for each. These can be used to adjust the water flow. We have solenoid valves here and here. The lower one controls the wash water into the flushing area of the tank underneath the screen. This one controls the wash water into the auger tank itself and also into the hopper. You can see a pressure gauge. There's 80 psi available now, at least when the water is not flowing. The question is how much pressure is available when the water is flowing, because the pressure will drop as a function of flow. This particular solenoid valve controls the wash water to the elbow, and you can see here the liquid discharge drain port. It's a 4-inch NPT thread connection, and there's one on both sides of the machine. One might be plugged, or they both might be piped in order to be able to clear away the bulk of the water. With a grinder as large as this 24-inch unit, the washer compactor tends to flow a lot of water, and in this case, both water discharge ports need to be open. We have a strainer here, referred to as a Y strainer. This has got a filter screen in it. It's the second strainer of the two. It should have a very fine screen, like an 80 mesh or maybe 100 mesh screen. Beside it, we have the primary screen for this machine. This is a basket strainer, and it will have in it a 20 mesh screen. We have a manual ball valve here. This can be used to block water into the system so that work can be done downstream to check filter screens for cleanness or for working on solenoid valves and the like. And then, of course, this is the wash water supply connection. We have another inspection port, and back inside here, this welded metal piece with this port on it, if you can see it, is a portion of the spray wash water manifold. This piece is a motion failure probe. It is watching the screw inside, or the rotor, to ensure that it's rotating. Down below you see a wheel, and this wheel is part of the roller base that the system is on. This is the drive end plate here as part of, the discharge end plate. That's part of the elbow, the discharge elbow, where the dewatering occurs. This business here is wash water connection point into the elbow. This is really only intended to be used on a periodic basis, especially when the system hits stage 4 operation, which suggests that the plug is too clean and too dry for the motor to be able to move it readily. From here, you can see on the back side some additional piping that was added as part of a wash water supply to additional wash water points on elbows up the way. For the most part, they should not need to be in operation if what's happening here at the dewatering point is good. As Danny had pointed out, if you can put your hand on here and it's not too hot, that would suggest then that the system is not working poorly. If it's hot, then that would suggest that there's excessive heat being generated, meaning there's excessive friction between the rotor and the plug, which suggests then that the run cycle or the operating parameters are not correct. Up here there's a taper tube, and the taper tube is responsible for delivering material down the way. The taper tube is in fact that. It tapers from 12.5 inches at the inlet end to about 14 inches ID on the outlet end. That's to relieve the friction against the plug so that it can travel neatly through to its discharge point. Thank you.
Thank you.
You're welcome.